Всем привет! В общем-то, меня представили. Я ML-инженер в команде Application Security это банка. И хочется не томить, а сразу перейти к делу. И... Ага, у меня не работает. Можно? Спасибо. Ага, он просто работает с задержкой, мне дали новый. Отлично. В общем, давайте представим ситуацию, что вы разработчик, который трудится над давно поддерживаемым проектом, кодовая база огромная, довольно сложная сборка, и в какой-то момент приходят безопасники и говорят, что в докер-образе с вашим приложением, которое сейчас бежит в проде рантайма, есть 1700 уязвимостей. И как бы так нежно намекают, что их надо исправить. И вот вопрос в аудиторию. Давайте скажем, поднимем руки честно те, кто не хотели бы этим заниматься. Так, отлично. То есть как-то избежать этой проблемы, делегировать другим, просто не замечать слона в комнате. Это в целом ожидаемо, потому что это требует некоторой рутины. И этот доклад будет про то, как мы в Т-банке внедрили LM-агента для того, чтобы помочь разработчикам исправлять уязвимости в докер-образах. И здесь будут действительно результаты на продовых данных. И доклад для тех, кто хочет прям вот понять, что работает, какие идеи лучше оставить в теории и не пробовать. Так что давайте начнем. И первое, про что хочется сказать, это предпосылки. Вообще зачем безопасникам может понадобиться сканировать ваши образа и какие проблемы это может вызвать у разработчиков. В общем-то, тут не обойтись без такого термина, как ECA, это Software Composition Analysis, да, то есть декомпозиция по на составляющие. У него много есть приложений, но безопасники в основном используют это для того, чтобы в общем-то, как-то оценивать риски, которые несет в себе программное обеспечение. То есть для этого есть куча разных open-source уже решений, которые довольно неплохо справляются с анализом тех же докер-образов, тот же Sift и Trivia. У них есть некоторые ограничения. Про эти ограничения я и мой коллега рассказывали в прошлом году, и мы даже предлагали наше исследование по тому, как можно эти ограничения обойти с помощью email. Так что в конце я дам ссылки на статьи на Хабре, которые у нас тоже есть. И если вы хотите узнать побольше про ECA, то милости просим. Ну а теперь давайте поговорим о том, как мы используем, значит, ECA у нас. А именно мы сканируем образа, которые есть у нас в регистре с помощью сифта и грайпа, и по количеству уязвимостей разного типа, да, и разного калибра мы формируем некоторый скор, на основе которого уже принимаем решение о том, блокировать образ или не блокировать, допускать приложение с этим образом в публикацию или не допускать. В целом довольно хороший выстроенный процесс позволяет контролировать то, насколько безопасные артефакты используются в разработке. Но это с точки зрения безопасников, конечно. Но вот тут сразу возникает проблема, что, вообще говоря, цель безопасников — это не просто оценить риски и прийти к разработчику с палкой и сказать, у тебя все плохо, а как бы действительно снизить риски. И здесь самый лучший способ — это пойти на координацию с разработчиком, то есть чтобы ему было выгодно и нам.
It's a matter of coordination with the developer.
Процесс выстроен таким образом, что мы просто скидываем разработчику какой-то репорт, у него есть там какой-то большой...
So the way it works now is we send the report, there is a large Dockerfile, and then, developers start getting lots of questions. Such as...
Можно, пожалуйста... Ага, все. А именно, да, то есть, во-первых, непонятная цель всего этого действия, то есть, ну вот я разработчик, я же могу заниматься тем, что пилить полезные
I'm a developer. I can be busy developing useful features, but, they make me deal with matters of vulnerability.
Отдаем разработчику результат сканирования образа.
Secondly, the process itself is non-transparent.
Этот компонент появился.
So they're making me focus on something which is not exactly mappable to the source code.
Зависимостей он может вылиться
this, whole issue of addressing vulnerabilities
И поэтому мы
can easily take up so much time. So we have decided to offer developers a solution that, you potentially would do stuff for them. And if that doesn't work, at least give them some insights about how they can address it. So before we do that,
нужно, конечно, посмотреть на рынок, посмотреть, что есть.
we certainly need to take a look at the market and what's available there.
То первое, что приходит в голову, это, конечно, да, Dependabot and Renovate.
So obviously, on the dependency side, there are Dependabot and Renovate, the time-tested solutions that support so many ecosystems that enable you to send pull requests from off the shelf, so to speak, for diverse remote hosts. And you may be thinking everything is fine, isn't it? However, there are some issues and constraints that we see here. And the first one
Dependabot это особенно актуально. Ему
is that Dependabot
конфигурация под специфику проекта.
requires configs for each and every project. You need to specify the system, the ecosystem.
Что тот же Dependabot, его довольно сложно настроить.
Dependabot, again, is hard to configure for local hosting because it has its own special Docker image, and it requires Ruby scripts. We don't really know much about Ruby, so we didn't appreciate that. And possibly the biggest limitation, and I've already mentioned Docker images, and Docker images mean
возможно, какие-то кастомные.
bigger image packages, maybe some custom builds. So Dependabot and Renovate don't know how to deal with that, because they have been developed and designed for, classic app builds for specific ecosystems. And if we're talking about, some custom build process, they're absolutely helpless. And there are several potential avenues here. One is the one that was chosen by Dependabot and Renovate, and this one is about expanding the list of heuristics and, do parsing of Dockerfile commands. This way you will have a predetermined list of algorithms that are easy to debug, but then it will be difficult to implement and difficult to support, because if you want to analyze some custom scripts, that would require some syntactic analysis of bash scripts, and that sounds like something sophisticated. So we can find, locations of bad components in the code, but you can hardly address them. I mean, you can try, but that would require your ability to analyze build logs, and not everybody can do that. That's why we believe it makes sense to take a different route. So, interestingly enough, LM agents are not too bad at analyzing code. So, LM agents should be able to analyze an unusual build of a vulnerable component and redress it. There are numerous pros to this avenue. It is really easy to write the logic of your agent in LangChain, and that's all you need to do. It's easy to support. Like if you found a corner case, you don't need to go inside the code. Very often you just need to tune the prompt. Also, you can try changing the build process itself, to clean the noise up, so to speak.
Анализа. Но, смотрите, это скорее не концептуальный, конечно, недостаток, а такой технический. Возможно,
Now, the next one is a technical limitation, not a conceptual one. So I assume that over time, it will become a matter of the past.
Вот подумав, конечно же, мы выбрали второй вариант. И
Naturally, we chose the second avenue.
первую идею, которая пришла в голову,
And we decided to implement the first idea that came to our mind.
идея заключается в следующем. Давайте используем
And it's like this.
для анализа
How about we use an agent to analyze the source code
то есть вот как на
with the view of
знаем команды Dockerfile.
discovering pre-installed components, so to speak. So these are the scripts and Docker commands. So this is how we're trying to create our SBOM. for further analysis purposes. So our first POCs with the LLM gave us the green light. We quickly saw that it worked reliably. There was no need for us to obsess too much with the LLM. Now, the first model that we tried, which was QN 2.572b, worked like a charm. So we gave it cat and find as tools, meaning that it was able to look for files in the repository and check them out. Let me explain the agentic logic right away, because after all, it's pretty simple. We gave Dockerfile commands as an input, and the objective of the agent was to give us the components that are installed with this command, also analyze the files there with the view of like discovering specific components. That could be a packet manager, it could be a script. And that's the logic. The result of the agent's operation is effectively a list of components with their locations in the code. What do we do next? Well, we scan it with a gripe, for example, for vulnerabilities. And then when we have those vulnerable components and locations in the code and the fixed versions, we can create a nifty merge request for the developer, which will highlight the vulns in his code. This is what it actually looked like in the production version. So it took us pretty little time to deploy it. We launched in production to collect feedback from developers. You should be able to see here that we were able to identify installation of Nginx, which had work of Dockerfile shown there. We also provide here a number of hints to the developer of what kind of vulnerability we address by doing that. We also gave them a link to provide us with feedback. This is actually it about the technical part of the story, and since we deployed this service in production, I should probably tell you of the structural and technical constraints that we ran across. We had limited GPU resource. We used our GPU capabilities during the day for higher priority issues. That's why we ran our pilot only at night. Now, we chose a repository based on the number of Docker files. The assumption being that if you have lots of Docker files, this must be the repository which contains the basic images. At least that was our thinking. This way you can actually, address lots of issues at the same time. So possibly the biggest constraint we ran across is that some users do not have the rights to bring a merge request straight into the repository, because we actually use the fork of the repository. And when you bring a merge request from a fork, you cannot trigger a pipe, though it really depends on the settings of the repository. And therefore, it will be difficult for you to check if the rebuild has been successful. So in the first iteration, we just decided to check, if the whole system would work if we simply give hints to the developers how to use it. Now, you gotta be careful with say the names of specific branches, and you have to check for regular expressions. And as you are collecting statistics in merge requests, I'm sorry, so I was about to show these stats, and here they come. In 2 weeks, we were able to generate 125 merge requests. For 102 components, we have been able to propose improvements, and only 2 merge requests were successfully executed, which means that we've developed a way to highlight for developers information on vulnerable components right in the code, regardless of the ecosystem.
Для каких-то дистрибутивных пакетов. Но здесь...
So it could be good for distros as well. But the statistics is pretty telling. Although we got some positive feedback from the developers, the figures are quite telling. And my first explanation for that is that our static analysis method, where we simply analyze the repository code, will have an SBOM different from the actual artifacts.
Пример, да, самый банальный пример, что если версия не указана в source-коде, то мы...
For example, if the source code does not indicate the version, we've got no way of knowing what kind of version it will be. So there can easily be discrepancies even at that level. Another constraint is that in the basic version, in the vanilla version, we did not take the source of installation into account. Let me illustrate it with a specific example. So you can see that a particular version of Git is being installed, and the version number itself, you will see that it's coming from Ubuntu maintainers. So this package is coming from the downstream, while the fix that we are proposing is coming from the upstream, which means that it's a false positive for gripe. And this is because when we developed or configured our gripe, we did not take into account that packages are installed through apt-get. So we need to only care about the versions coming from Ubuntu maintainers. And it's obviously a fundamental issue. And there is a workaround, no doubt about that. You can, for example, take package source as yet another factor, but that way we will be pretty much copying the logic of SIFT. SIFT is actually good at identifying sources as upstream or downstream, and it doesn't generate falses there. So if you scan the same project, it will not generate falses. Well, we do. So this is certainly a constraint. And we decided to stop here. We decided to sort of look retrospectively at what we have done and potentially change our approach. So LM agents have a pretty good potential. We haven't obsessed too much with configuring them, and from the very beginning, it worked in a pretty reliable way. Now, we learned in the School of Hard Knocks something about infrastructure limitations, and we'll certainly remember this lesson. And we also see that the static approach to code analysis comes with lots of constraints. So, for the purposes of analysis, we need to take into account the scanning results of the ultimate, output artifact. Now let's...
I'm sorry.
Let me give you a kind of a fresher look at that. Rather than, looking at Docker files, which has been my attitude, so to speak, so far, let's instead look at the results of a scan of a complete artifact and then analyze every vulnerable component in its own rights and see if it can be addressed easily. So that would mean that we are sending these components to our agent, and then based on its analysis, we'll try to generate merge requests. So if we're doing that, which we actually did, we discovered that deploying a POC that would give us a pretty good quality right away was very difficult. We actually failed at that. That's why we had to change tack. Previously, LM worked like magic for us, and here we decided to grab the same production data but apply it differently, without getting in the way of developers. Because, everything we needed from developers, the feedback we have been able to collect.
И в целом мы решили, провести больше экспериментов, собрать данные.
So we have decided to run more experiments. We took 2 models.
И здесь уже
Now we use VLM server as an inference, and we were inspired by SWEH in article in terms of selection of tools. Now,
команды из Command Shell, чтобы было понятен смысл этих тулов.
I'm telling you the names of the shell commands to make it clear what each tool is doing. But if you want more details, please read the article.
Я только скажу, что мы
Let me just say here
все тулы на LangChain, никаких MCP протоколов и
that we have been running all the tools on LangChain. We have not been using any MCPs or whatever. because it turned out that it is much faster to do things on LangChain as opposed to creating your own servers and addressing unification and scalability when you're trying to combine agents with tools. We had a specific tool, we had a specific experiment, so LangChain made a lot of sense.
Здесь почему вообще, давайте обсудим, почему у нас появились некоторые проблемы с тем,
Now let's discuss.
Ну, в отличие от предыдущего подхода, вот в прошлый раз все получилось сразу.
What the differences are compared to, the previous avenue, so to speak, because here we had to redesign so many things.
Отчета. И, возможно,
So we have a component from the report as an input. And it can be coming from the basic image, or it can be on top of the basic image, and it can be installed implicitly or explicitly. If it's implicitly, it could be installed as a dependence.
анализировали только те компоненты, которые
Previously, we would only analyze the components that were installed explicitly.
Забегая вперед.
This time, we don't know what kind of component it will be. It should be easy for us to filter out the components that are associated with the basic image. And as regards explicit and implicit installation, our agent has been hallucinating crazily. It for some reason, thought that the implicitly installed components were explicitly announced somewhere, which they were not.
Во-первых, мы не анализируем.
So it's important for us to agree on the constraints here. We are not analyzing components from the basic image. If a component comes from the basic image, then we gotta apply it all to the basic image rather than an additional Docker file. We'll also try to edit the components which are installed explicitly because it's easier. If we manage to do that, we can try attacking the more difficult problem.
Объясню, как мы, проверяли.
Let me explain the hypothesis and let me explain how we tested it and developed our data set. Our primary hypothesis was that our LLM agent would be able to identify the component type and the command that actually builds or installs it, and should be able to successfully change the version for the explicitly installed ones. So we took 30 different images. So there were 206 components with high level and critical vulns. And we chose those ones that, because they're interesting, they get a lot of attention.
Да, и что касается точности срабатываний, как правило,
and as regards accuracy, when we have highs and crits in the report, in all probability they will be there. We do have fewer false positives in a population like this. So the task here is to check whether the agent has been able to analyze the component for its genesis, so to speak. We have introduced here some reference points that can support us in deciding whether the agent has done a good job or not. So the agent should identify the type of the component, whether it's explicitly or implicitly installed. Also, it needs to tell us exactly which command installed that component, even if it was installed implicitly. At least it should try that. So what kind of data we use for that? Obviously, Dockerfile name, path there, component information included version, name, and names of files where it was discovered.
Неочевидный пункт — это команда, которая породила слой, из которой пришла компонента.
And another thing is the command, the instruction, which actually generated the layer that component came from. So the repository of the Docker file can be discovered by the tools of the agent.
Подробнее нужно рассказать про то, как мы их готовим.
So let's talk about how we prepare this data. Look, we're going to talk about pre-processing. Usually in the reports, we see the hash layer in which the component is stored. We know the sequence of hash layers, how they were represented in the image, but we don't want the commands which generated them. However, the command which generated each layer can be found in the config that is stored in the Docker image. So basically, knowing the list of commands that generated each layer, we can map the needed hash layer, and thus we know which command generated the vulnerable component. And since we have the Docker file, we can easily understand which component came from the base image and which from above it. So we will correlate the history with the commands in the Docker file. By doing this, we will filter the components which came from the base image and work only with those components which had an explicit installation command. It's also worth mentioning that when we put together the image, the Docker file doesn't have the RGs as EMVs easily discoverable, but we can find them in the history of the commands that created the layers. Talking about the args, the arguments, all the images that are published in the register are published through GitLab Sci. So we collect all of this and put it into a new tool for our agent so that it could see the values of the variables at the moment of assembly. So now we can switch to the logic. As I mentioned before, we prompted a lot, we experimented a lot, we researched a lot, and this is the most useful, the kind of our best scheme. It ended up being not so difficult, in fact. This is the first level of analysis where we define the control point. It is divided into two phases. We have to determine the Docker file assembly point. So if there is a copy command, then it's clear that the command which generated the component is the one from which we copy, right? And it's in the stage where we take the copying, so it's easy enough. However, if a command generated a layer in which we discovered a vulnerable component, if the command is run, which starts a difficult mesh script, then we have to pay attention to the origin of the files that constitute the script. Thus, the first phase narrows down our discovery environment down to the stages where the vulnerability could have potentially occurred.
Мы готовы к следующему этапу, где мы на вход.
So now we're ready to the next stage. On the next stage, our inputs are those stages. We say, oh yes, we have a vulnerable component, but we don't ask to determine its explicit or implicit nature, but we rather ask how this command could have ended up in the image. So after this reasoning phase, we get the location type and the command type.
Ну и понятное дело, что в случае явной установки мы еще, конечно, попросим.
It's clear that in terms of explicit installation, we will be asking also for the location. That will give us the version which we are going to correct. So let's talk a little bit about the correction. How is this done? Again, it's pretty straightforward. Once the first analysis phase is over, we have the components which have been installed explicitly. We know their location. We also have the fixed version that is coming from Grape. So we put this in as input material and let agent to do it with a new instrument, with a new tool, edit. It allows basically to put different code in the snippet. Thanks to that, the agent does the necessary changes in the code, launches the PyAssembly, and after the assembly, and we also did that ourselves, so we had about 7 iterations of such assembly. So we think that if the agent wasn't able to do it in 7 iterations, then there's something wrong with the component. The developer probably would not want to do that if the developer is to blame for the initial error. So basically, let's look at some specific examples of how it worked. All right, there is a component, GoLand, okay, crypto. It talks about the dependency of Gripe and Sift. And the agent here did its job with identification and localization of these commands. We saw that this was a copy of Ubuntu Builder. Phase 2, we only looked at the Ubuntu Builder commands on that stage. And the commands such as run and code here, there are binary sifts and gripes, and the info which we provide as input has information about in which specific image files we have found the vulnerable component. So the agent did his job well here, as I mentioned. It localized the commands which brought up the implicit vulnerability. This is another example. The components here, it's a Debian package. It was not mentioned in the Dockerfile anywhere. And the first thing that the agent did here, it looked for mentioning of this component in different files, found it in zips, which was next to the Dockerfile, then realized that the final file doesn't have mentioning of this component, and then it switched over to sifting through the files which are generated by these commands. It found the script. This is not an easy one, to be sure. It works with different distros. And though this script was parameterized quite heavily, so it's not really clear from which file it takes the information that it works with later. However, we were able to identify this command and take care of this component after a number of manipulations. So, of course, we want to see some numbers. We mapped the data set, we have the component, but we have to have a benchmark or a baseline, if you will. So let's take 3 commands as baseline. Grep. Let's try to grab the components in the type, if there is a version and a name. If there are, there indeed will say that the component has been installed explicitly. If not, that will know the command which did it.
И в качестве эвристики фикса давайте просто будем заменять все вхождения.
And again, as an heuristic logic, let's switch everything to the latest Gripe versions. So this is a basic baseline. So let's look at the metrics.
Ну, смотрите, Квен
The first thing that you see is the
генерит больше
bad quality of QM.
в ходе, что и лама.
It
У него
generates a lot of tokens on the same
контекст. Он любит уходить
part, Llama, on the same port at Llama. Its context usually is finished quickly, and it likes to recall the function. So this is not a very good situation. At the same time, if you look at the baseline,
чтобы определить,
you'll see that it did a good job of determining the type of component, whether it was installed explicitly or implicitly, that was to be expected by the way. There's nothing difficult in it. And as far as determining the command of installation and assembly, we had 0.83 and 0.70, which tells us that the agent pretty much fulfills its task. It analyzes the assembly, it analyzes the command. And if we talk about the correction with the reassembly, so we were able to correct 11% of the criticals and 15% of high vulnerabilities. One would think that this is a not large number, but I'd like to note that out of 206 components that we had, only 25% are installed explicitly. Only we worked with those. So I think we have a 50% success rate, which isn't that bad. I didn't want to cheat and show you the component that we worked at, because we want later on to work with the implicitly installed components as well.
Возможность отдать логи в обратно в агента.
So the possibility to give the logs back to the agent and to correct, to adjust its work, boosts the quality a lot. There may be some dependency conflicts, compatibility logins, conflicts.
Это что касается результатов в цифрах.
This is kind of the results in numbers. As far as timing goes, let's recall that we had about 200 components so it's 6 components per image. So analysis, the primary analysis, took about 1 minute and seconds. So 10 minutes per analysis, and then you have to correct that. And since the correction time, assembly pipe takes about 45 to 50 minutes, regardless of its success. But at the same time, the analysis of one image, one Docker file, can take up to an hour. But basically what will happen during this hour is reassembly and kind of rewriting the script and waiting for further instructions. So take this into account as well when you think of timing. So different features and tricks of the trade, so to speak, know-hows that we came by when we worked with the agent. They're giving you hallucinations, right? So we wanted to validate the model's output in a way that we could check whether there was hallucination or not. For instance, when we were asking for a command and a file, we always checked that this file indeed contains this command. If there's no command like that in the file, then we continued the dialogue with the agent, asking it to correct its result, its answer.
Та же история про то, что мы сначала там пытаемся выделить стейджи, только потом работаем в рамках этих стейджей. Это тоже на самом деле.
Again, the stages of assembly.
Вот сюда же я отношу историю с тем, что
allowed us to get rid of the hallucinations. The
то, что моделька там с первого раза
assembly logs can correct the
но поскольку у нас есть целый
analysis errors really well. And then again, since we had 7 iterations, 7 tries, it in
второй пункт я выделил, это то, что нужно следить за размером файлов.
second trick is the size of the files. So this is an apparent thing.
Агент производит анализ компонентов.
So when an agent conducts analysis of a component,
Пытается локализовать
trying to localize its origin,
то, где она находится, он пытается зачастую читать какие-то большие лог-файлы.
the agent tries to read very large log files,
И
poetry log, for instance.
мы боролись с этим тем, что не
So
выводили,
basically,
чтобы не съесть весь контекст.
we tried to fight that, but not
Попробуй потребовать по этому файлу, я тебе его видео
uploading
покажу.
all of these files.
Вот опять-таки, ссылаясь на статью из Agent, они боролись с большими файлами тем, что дали инструмент скроллинга, и тоже, по сути, там агент, он мог найти какой-то порт.
Instead, we made the grep commands. If you read my article, and an agent could basically find a reference point in a file and go up or down, we were able to do without it. So if an agent wants to look at a specific large file, we understand that it is looking for something and has reasons for that. And the baseline experience, finally. We saw when we talked about the metrics that the baseline is good at determining whether a component was installed explicitly or not. So don't forget about that. So use the grep function and use just one entry point. So we basically are breaking this into production. We already tested it in the lab environment, and currently we are at the final stage of the shell development. We think of future improvements and talking about the fixes. Of course, we will fix the components which were installed implicitly. Gripe and sift example that I invoked already is useful here. If we could give an agent all the information about the releases of the soft that was used at the GitHub, we could have tried also to correct the components that were installed implicitly. Talking about the renovated Dependabot, we had a lot of different ecosystems, from Python to distro packages. So we also have Java, and the model was working well, but there were some cases when some standard assembly of the is enough of Dependabot and Renovate. And it's clear that if we have a known pattern, we'll have to stick to that. There are some basic cases, and Dependabot and Renovate are good at dealing with this. We have to think about acceleration, because in our approach, we, on the first stage, analyzed just one component. We only had one dialect with an agent, right? There was a dialect per component, and then we kind of batched them, we packaged them, and went them and sent them for the fix. I think we can also group an agent, or rather use one agent for several components. Maybe this will not give us additional speed, but I think this is something that we should look into, at least. So let's move towards the conclusions. We looked at two approaches, two avenues. One of them was good in the proof of concept, and we wanted to bring it to the production, but there we had an unexpected problem. This experience was good. Now we know structurally where these problems are. We know how to launch the pipes automatically without asking the developer for it. So we will ask the developer for subscription rights that would allow us to do that. So it's kind of the combat style decision. If it happened at the first go, it would be, of course, a great victory. So instead of that, we took the second approach, tested it in the lab. So taken into account All things considered, I think this is a very good development of Dependabot, because right away, just using an agent, we took care of 11% of critical and 15% of high. So this is a win-win solution for business, for developers, for the security professionals. So guys, don't be afraid. Try, and you'll get it. Everybody is very skeptical about LLM agents right now, so are we, but this is healthy. Okay, but don't bring this skepticism into your, rather put this skepticism into your lab practice rather than into your negative approach. Okay, so thank you once again. I'm ready to answer your questions. Pavel, thank you for the presentations. If you want to ask a question, please use a mic. Mics are on both sides of the hall. And while we're waiting for those who want to ask questions, I'll have the first night right, so to speak, right? Okay, you mentioned that at a certain moment of research or implementation, you had the resource conflict. Resource usage conflict. And I saw that you had an automated language checking through matching. Did you try to run smaller models on that? No, we didn't try it. It's a good question. We didn't try smaller models, but still, of course, when you run an experiment, you want to see the green light to understand that the experiment is working. LLM has worked, and then we will do the product solution, and on that phase, we will test something. So basically, our major goal here was to get the red light, so to speak, to see that it's working. Hi, my name is Dmitry. Thank you. It was a very interesting presentation. If we talk about the implicit dependability, in LLM, you use a lot of resources in order to feed context into the model and understand how this dependability arrived. But then you report to the developer a critical vulnerability. Although, the way I say it, you are not importing the dependencies rather, and it's harder for you to later on correct the thing. So maybe it makes sense not to report the GRIF, but just say, you know what, in this code line, you have implicit components A and B, and this is our solution for that. So how do you import this dependencies so that we wouldn't have to use Sherlock Holmes later on, but to do it by applying classical tools, run on smaller resource base. So you mean, if I may specify, from a gripe report, you think that this component is depending on that one? No. You mapped by having conducted the analysis of the layers image of the image. You have mapped the dependencies, right? The vulnerabilities, but you can't parse them. Since you can't parse them, so this is the biggest problem for you, right? You can go to the developer and say, look, it hurts me to look at this dependency, but take the standard input flow, and this will take care of the pain. We said that you have 3 criticals here, and the next time we will be able to detect them much quicker because you would have employed our security tool.
Вот интересный вопрос. На самом деле интересная идея.
That's an interesting question and an interesting idea. I already mentioned that in its basic variant, we will report to the developer that they are
Вообще, я уже сказал,
downloading or installing a component which has a vulnerability with it.
возможность получать информацию о
This can be taken care of if we give
компонент, который становится явным.
to the agent a tool which will analyze the vulnerabilities which were, or rather the components which were installed explicitly. It won't work every time.
Пакета. И тут, наверное, да, вот стоит взять идею на вооружение, что это тоже дальнейшее развитие.
And I think that this is a good idea to think about the restructuring of the assembly process, so that if something can be done explicitly, it should be done explicitly.
А фикс именно структура.
So basically, maybe the fix should be aimed not at the vulnerability itself, but at the structure. Yeah, we want to have to apply a more structural approach. People who cannot write good Docker files should benefit from our recommendations of the sort.
Так что да, это тоже полезно. Спасибо за вопрос.
Yeah, thank you very much. That's a good question.
Давайте с правой стороны теперь доклад. Ой, вопрос.
Okay, a question from the right. Hi, thanks a lot for the report. I also wanted to ask you about the plans that you might have for the development.
Зайти с двух сторон, можно зайти со стороны.
So maybe you approach it from both sides. One of them being that the developers could train LLMs people and other way around. In other words, they will provide a model that would feed to LLM the comments to the MR or merge request, or you can do it in the other direction so that the LLM would kind of explain things to the developers. I like your idea. Yeah, we will look into this direction. I invite you to our stand. It describes this technology. Yeah, I think we have to nurture in the developers the practice of more safe-proof assembly. The problem is that we cannot conduct an experiment. It looks too difficult. That's why we decided to take an easy thing first and then move from the simple to more difficult. But yes, the kernel of your idea is correct. We will share our insights with the developers. What about the other way around? If so that the developers could tune LLM, could you specify? Could you clarify?
Ну да, наверное, вы ответили, что, допустим, вот именно вот через, допустим,
Well, yeah, I think I got it. Yeah. Comments and merge quests. I think you've already addressed that.
Да, то есть именно вот в режиме диалога.
Ну, кажется, что это сложно инфраструктурно.
It looks like infrastructurally it's not an easy thing to do. You have to have access to the whole dialog information. So here the developer came and said, okay, agent, go ahead, keep working. But yeah, well, the memory banks are on the market right now as part of the integrated databases that the agents will use as well. So this is kind of the MCP continuation. I read the recent research paper on that. So this is something that I think could be useful here. All right, well, we'll pay attention to it. But basically right now, in the base variant, we don't work with the developers' comments. I think we need more research and more specific things. It will give us better production value. But we'll keep this in mind. Thank you.
У того же микрофона вопрос.
Okay, the same mic. A question, please.
Не смог поднять стойку. Добрый вечер.
Good evening. My name is Denis. I have the following question.
Описано, как минимизировать галлюцинации модели.
You told us how to minimize the model's hallucinations.
какие-либо механизмы
Have you thought of any mechanisms
агента от, к примеру, prompt
of AI agent protection from prompt injections
в самих компонентах, либо в
in the components themselves or in components metadata? Oh, this is a great question. Of course not, because we didn't look that far.
Вся схематика и как бы архитектура
This whole schematics and architecture of our decision
она работает за которым
doesn't allow any injection. It works with a ready depository, with a ready gripe report, with ready Docker files. If you are a developer which have created a Docker file with injection, yes, but no. Right now, this is an internal solutions. We haven't presented it to the public yet. So far, we don't think that people will do harm on purpose.
Возможно, если команда
But this is possible if the developer team is hurrying to bring the prod to the market. Okay, well, our job is to make recommendations. Your job is to take them into account. Otherwise, you, as production team, will lose your job.
Здравствуйте,
Okay.
спасибо за доклад. Меня зовут
Hi, thanks. My name is Dmitry.
больших вопросов. Первый
A few small questions.
популярность сервисы проксирования
Proxy services are becoming
и
more and more popular.
с ними, насколько хорошо он их определяет, самое главное, насколько
Have you tested any of these proxy services? How well are they doing?
он его задетектит или нет?
If the URL is lying on the proxy server, will it detect it?
Новую версию,
And will it direct it to the GitHub, or will it live in the old repository? Well, this is an infrastructural problem, I think. Yes, I think you're referring to internal infrastructural problems, or packages rather. Yes, there are some registries there, but we haven't looked in that directions yet. We use gripe, and gripe doesn't tell us which components we have in our banks. So, at least initially, we are operating by what's given us from the outside. So we have that. I'm not talking about the internal infrastructural packages.
Это же проблема, опять-таки, инфры и то, как пакеты тянутся. Мы не занимаемся...
This is a problem of how the packages arrive to us. If we arrive, when we pull the package through the proxy, it's not our task. We have a report about the image scan, and we have to minimize the things. Another team does that.
на ту проксию, которую надо, или он создаст ее на...
So if that other people create an MR, will they direct that MR to the right spot? Will there be no problems with outside register?
Там как раз ограничение стоит на то, что он не может менять...
I think all we have to do is to change the version. We cannot change the address of the package where it came from.
Нам нужно изменять имя, там, источник компонента. Вот. Понятно примерно?
Да, понял,
Все, окей,
спасибо.
спасибо.
И
All right, thanks a lot. And
Я
the second question that I have.
направляете это на репозитории. А если
So basically, you put this on the repository.
там при сборке
Is there a chance to make it work within the pipeline? And when the assembly happens,
проводить более человекочитаемый отчет,
to analyze the kind of the bottleneck
Имеется в виду под более человекочитаемый репорт.
and finally give a more readable
отчеты, которые трудно читать.
report. What do you mean by more readable?
Ну вот,
Yeah, so that it wouldn't consist of raw material.
что вы поставили, это
Yes, indeed. One of the tasks that we have is to map the reports that are done by Trivia or Gripe in code.
используем то, что выплюнул нам...
So we're not determined by what we have. We go by,
вот тут у тебя
we should be determined by what the agent
мы предлагаем
gives us, right?
X, и вот так. И
Like these are the scripts, these are the criticals, these are the fixes.
весь пайп,
So why are we
весь пайп разработчика, который у него есть репозиторий,
pushing this to the LLM? We don't want to touch the developer. We want the LLM to take care of it by itself.
Теперь нужно выбрать
Thank you very much. Now you have to choose the right. Can I ask another question? Unfortunately, not. We don't have time for more questions during this session, but you can always find this gentleman somewhere in the corridor. Okay, so the best question that I heard was about restructuring the assembly process. Somebody, I think the second person who asked the question asked that specific question. I remember my response. Yeah, let me recall the question. The question was about implicit component, right? So that we would make assembly in such a way, restructure the assembly in such a way that all things implicit would become explicit.